Hello everyone. In this video, we are going to talk about chapter 13, section 13.5. We are going to break our equations of motion into the normal and tangent components. So in the past, it's always x and y are perpendicular to each other. In this section, we are going to break it into the normal direction and the tangent direction. So let's take a look. The normal direction will always be points toward the path center of curvature. In a circle, the center of the curvature is the center of the circle. Tangent direction, it's always going to be tangent to the path, usually set as positive in the direction of motion of the particle. And then so in case under the condition that if you see a problem in 3D, you will also see the binormal direction. But without the third direction, right? If our problem is in 2D, so this breakdown is very similar to our x and y, the ij component, right? But with the binormal, we'll be adding the k component. So in the vector direction, you have f equals ma. So we have the tangent direction, normal direction, and sometimes you may have the binormal direction, depends on your problem. And then similar to what we do on the xy direction, this vector equation will be satisfied provided the individual component of each side of the equation are equal, resulting in the two scalar equation ft equals mat and Fn equals man. And since no motion in the binomial direction, we can also write F binomial equals 0 under the condition there's no binomial direction. So normal and tangent acceleration, tangent direction will always be changing, deal with the rate of change of the magnitude of the velocity. So that's what we call the tangent direction. Normal acceleration an equals v squared over rho, where the rho is stands for the radius of curvature. And remember, an always acts toward the path center of curvature, so Fn will always be directly toward the center of the path. And in under the condition, as we recall, if the path of a motion is defined as y equals f of x, if it's a function, y is a function of x, the radius of curvature at any point can be obtained from this equation right here. We saw this equation before in our previous videos. So using the anti-coordinate when the particle is moving along this curved path, we're going to establish the n-t coordinate system on the particle. We're going to draw the free body diagram and kinetic diagrams of the particle, and then the normal direction will always be inward, positive n direction. Tangent acceleration an may act in either the positive or negative t direction. We're going to apply the equation of motion in the scalar form and solve it. And it may be necessary to using this kinematic relation again, at equals dv over dt or v dv over ds, and an is equals v squared over rho, rho being the radius of curvature. Let's take a look at some examples together. We have this ball, right? 10-kilogram ball has a velocity of 3 meters per second when it is at A along the vertical path. We're looking for the tension of the core and the increase in the speed of the ball. So we're going to first draw our free body diagram. Okay, at 45 degree, right here at that point, free body diagram shows all the forces being applied to the particle. In this case, you have a tension at T, right? It's the same direction as the cable, and you have the weight pointing straight down. Kinetic diagram instead, F equals ma, right? Free body diagram is your F, and then your A over here is man and mat. We break it into two different directions, which is the normal direction and the tangent direction. Now let's write our equation. And again, our equation is going to have two of them, tangent direction and normal direction. So over here, your t is totally along the tangent normal direction. And then that w, we can break that w into the normal direction and the tangent direction. So this w, since it's all 45 degree, right? So this one, w cosine 45 or sine 45, same thing, and the t together, that will be on the normal direction. And the other part, w sine 45 degree, the other part of it will be the tangent direction of the weight. Okay, so t minus w sine 45 gives me man. We plug in an equals v squared over rho. And then also on the tangent direction, w cosine 45 equals mat. Putting these two together, we can solve our tension. What we're looking for is the tension of the core and the increase in the speed of the ball. So, in other words, we can look for we understand from here we can get our tension, and then the second equation we can get our AT. AT is the tangent direction acceleration on the tangent direction. So it's also the change of the magnitude of the velocity tangent direction. So AT, tangent direction of the acceleration, deals with changing the magnitude of the velocity. So that's how we get, AT equals dv dt, which is 6.94 meters per second square. Next example, I have this little boy that is sitting on the swing going back and forth, right? We know at that instant theta right there is 60 degree, and then the boy's center of mass, G, experienced at the speed of V equals 15 feet per second. We're looking for the tension in each of the two supporting core. That means in this diagram, we do not see two cables pulling the boy, but you will need to understand that at the swing, you will have two, usually there will be two cables pulling the swing up. So that's why there's two cable support there. And then we're looking for the tension in each of the two supporting core of the swing and the rate of increase in his speed at this instant. Okay, so free body diagram showing the tangent direction and the normal direction. And then the 2T, look, in our free body diagram, we're going to have 2T because I have two cables pulling the boy. And then the weight coming down, I have it 60 degree. I can break that weight into along the tangent direction and the normal direction. So this way and that way. Okay, so let me redo that real quick. The arrow was ugly. So normal direction and the tangent direction. Okay, so now writing our equation, we're going to put our equation into the normal direction and the tangent direction. Normal direction, I have 2t minus w sine 60, which we break our w into this way and that way, right? So sine 60 gives me that way. And then using an equals v squared over rho, we got w equals 60 pounds. And also we can calculate t equals 46.9. Along the tangent direction, you have 60 cosine 660, right? Only the weight on that tangent direction, that is the only force acting on it. Okay, so putting that together equals m times at. There's my mass times acceleration on the tangent direction. That will give us the acceleration on the tangent direction. Last example, I have this vehicle traveling over a hill, which this is the hill is a parabola, right? Function, parabola function. And when the car hits point A, velocity equals 9 meters per second, acceleration equals 3 meters per second square. Find the resultant force and the resultant friction exerted on the road at point A by the car. So we're going to draw our free body diagram. At point A, you have weight coming down. Friction will be along the path, but going the opposite direction of your motion. Normal force will always be perpendicular to the surface. And then your kinetic diagram, you have your AN, MAN, and MAT. We're going to write our equation again. The weight over here, we're going to break our weight into normal direction and the tangent direction. Normal direction and the tangent direction. So when we write our equation, this keep on giving me that big line there, which I don't like. So in our equation, right, normal direction, you have W cosine theta minus n equals MAN. All right, plug in AN equals V squared over rho, which is the radius of curvature. We have a relationship between the normal force cosine theta and the rho. Along the tangent direction, we have W sine theta minus F equals MAT, and using W equals mg, AT equals 3 meters per second square, which is given to us. We have a function of F, relationship between F and the theta. And keep in mind that this F right here is your friction in between the surface and the vehicle. We know that this fy equals f of x. This is a function, right? Parabola, it's a fy is a function of x. We can use this equation right here. We see it in the previous slides, right? And then so we are going to take because we need a dy dx, right? We're gonna, and then the first and second derivative of y with respect to x. We're gonna do that and plug into this equation to find the row radius of curvature at that moment at x equals 80 meter. And then to determine the theta, we can use tangent theta equals dy dx at x equals 80 meter. And then we can find our angle. Okay. And then plug that back into the theta. We plug the theta and the rho back into our equation 1 and equation 2. We can get our normal force and the friction force between the vehicle and the surface. That's all I want to show you in this video. Thank you for watching. Hope you find this video helpful.